Yeah. Okay. No, so there's no, so when it's most similar word, the rule is if the similarity cannot be computed, it is considered to be -1. So there could be situations where you cannot compute any of the similarity, and then it's just a tie and you return the leftmost choice. Or you could have a situation where you cannot compute the similarities for some but not others because some of the targets are not there, and then it's whichever one is the smallest.
Choices never end.
Choices never. So that means it's a tie. So you return the leftmost one. So effectively the first one. Yeah.
So how do you know if our fully kind of satisfies the complexity?
I mean, one way to do would be to analyze it, but in practice, if it runs in the novels, there is no way that it does.
If it ran the novels and it passes the test cases on.
I mean, the test, yeah, I suppose if it doesn't pass the test cases, it could be like the correct complexity, but not incorrect output, so that wouldn't count. But yeah, like it's not possible to get the complexity wrong and be able to actually run through the novels. Yeah, just because it takes so long.
Yeah, that makes sense.
Yeah.
I have a question about the complexity.
Okay.
So is it like if you have O(n) squared,
Right.
that is the bare minimum, or like will you lose marks for O(n) squared? Like
O(n) squared? No, that's not the minimum. That's above.
no, like the bare to not lose marks.
It needs to be below O(n) squared, where n is the number of words.
N is the number of words in the text.
Of distinct words. Yeah, so you cannot do O(n) squared where n is the number of words.
Okay. So if we are iterating through each sentence and
then that's different because the number of words per sentence is limited.
Because currently the way mine is set up is I'm iterating through each sentence, I'm iterating through each word in each sentence.
That's fine.
That would be O(n) squared.
That would be k squared times n, where n is the number of sentences and k is the number of words per sentence.
If I'm only doing one pass through each sentence, then it would be all k, right?
Well, I mean, presumably you are like looking at pairs of words within the sentence, so it's presumably k squared. But it's presumably
Okay. And so we need to make sure to somehow get it less than k squared.
No, you need to make it so that it's less than O(n) squared, where n is the number of distinct words. So that's like a different thing, right? So the other possibility, like what's O(n) squared, is if you say, I'll get all the possible different words, and I'll try all the pairs of all the different words in the vocabulary. So I have like 10,000 words. The vocabulary, I would try like 10,000 squared pairs. I'll compute the occurrence count for each. That would be O(n) squared.
Okay, so this isn't O(n) squared. This is good enough for the assignment?
Yeah.
Well, I currently have.
What you said, I mean, what you said sounds right. But I will also say, like I said, when I was introducing the thing, it's just not gonna run if you do kind of the wrong kind of O(n) squared.
Okay, and it's only for the build semantic descriptors function that we need to reach that time complexity.
Right.
So, like,
yeah,
this, like percentage.
So I can check your code because the lecture is starting again. Yeah. Okay. What? All right. Hi. 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 Hello, everyone. This is me yesterday in San Diego. Yeah, looks the same. Just, just like to let you know, it's 15 degrees in San Diego. Pretty nice. I was disappointed. But I'm glad to be back here though. It's good. So what I want to do today is do a little bit of complexity and then do a few fun things, some of which I'll mark out as not really on the exam, some of which I'll mark out as on the exam. The first fun thing that's potentially on the exam is quiz 12, the last of the quizzes. Are you here? So it's a good thing that this one has a single answer, because yesterday I looked at the results of the quiz, and let me tell you, not everyone got the second question right. So, all right. But the first one should be easy. So this one, if you went to lecture yesterday, should also be easy. So who says O of 1? Says O of n. O of n squared. O of 2 to the n. Okay, thank you. I think most people did not put their hand up, but it is of 2 to the n. I want to do it in detail because I want to do a variation on this, which well, I'll tell you which part of that is going to be on the exam and which isn't. So we are over here. So again, kind of what do you do? So you go to the shapes of the col trees that you have. We made like a nice handout. And you ask kind of what kind of col tree is it, right? So okay, so what kind of col tree is O of 2 to the n? Well, you start with power n, right? So you start with this, and then you go from n to n minus 1, and here to n minus 1 as well. And then here you go to n minus 2. And so on, you'll have an n minus 2 here. And then eventually you'll get to O once, right? We now say, okay, I make sure that each call actually takes the same amount of time. I made sure of that, but making sure that I'm always operating on floats. This is why I converted this n here to a float. So float addition always takes the same amount of time, doesn't matter the magnitude. And now I'm just counting how many calls there are. And the answer is, well, like 1 over here, and then 2 over here, and then each call here spawns 2, so that's 4, and so on, up until you get to this point. So this is, 2 to the 0, 2 to the 1, 2 to the 2, and so on. So this is 2 to the n. And then you're saying the total number of calls is 1 plus 2, and so on, plus 2 to the n. That is the geometric series. So you got to know the geometric series, the arithmetic series. This is 2 to the n plus 1 minus 1 divided by 2 minus 1. This is 2 to the n plus 1 minus 1. And this is O of 2 to the n, because this is just 2 times 2 to the n plus 1. So O of 2 to the n. All right. Question so far? So again, kind of on the exam, so you do get those kinds of things all the time. The thing to know is that there just aren't all that many col tree shapes that you could be asked about, right? We basically had all of them, all the common ones at least, just on the handout that you got yesterday that's posted on the calendar as well. All right. So that's that. So I want to go now to something that's a little bit different or a little bit the same, depending on how you analyze it yesterday. And that's the Fibonacci one. So we'll say if n is small or equal to 2, return 1. Otherwise, we return fib n minus 1 plus fib n minus 2. Okay. So the Fibonacci sequence, like, well, it's defined like this. And the way it works is you have like 1, 1, 2, 3, then 5. So the sum of those last two, and then the sum of those last two, and then the sum of those last two, and so on. Make sense? Kind of discovered or defined by Fibonacci. There's like all sorts of ways in which it appears in nature, stuff like that. The sequence, right? So, okay. So what's the runtime complexity of computing it like this? So here is an attempt at an analysis that, I would probably do if I were just starting out. I would say, okay, so we start with n, and then here I'll make a call to n minus 1, and I'll also make a call to n minus 2, right? And then here with n minus 1, so I'll make a call to n minus 2 over here. And I'll make a call to n minus 3 over here. Over here, there would be a call to n minus 1 again. And then also to n minus 4. And then eventually I'll get to like whatever, like 2s and 1s, basically, right? So something like this. All right. So one issue here is that this is not a symmetric tree, right? So in fact, like there would be a 1 here, but then